Okay? That's good. Thank you. You guys want to pass in your homework too? And the rest is online, I hope? Yeah. That's right. Today is the first day of homework submittal. Habits you will enjoy and pursue over the course of the semester. There's another homework due on Thursday. And since you're handing the homework today, the homework only for those who haven't taken the first part of the course already. No, the homework this time will probably be different than the homework last time. So you do not want to miss the opportunity to enhance your knowledge of the subject by not doing the homework this time as well. And I wouldn't want to deprive you of that privilege. But of course, it's going to be an onerous task for me to grade the homework, but I'm willing to do that. All right, that's here now? Okay, good. Stockholm, good afternoon to you, and again, you have some homework due today, as well as Thursday. To begin with, I'm going to talk a little bit about the big picture of what we're going to do over the next few classes, so we'll have sort of a roadmap of where we're going, and therefore I hope that we'll not get lost in the details of the bumps and side trips that we may take from time to time. But before I even do that, let me pause and see if there are questions. Stockholm, do you have any questions you would like to ask before we begin? And the answer is no. We are going to give the people in Durham a chance to ask questions too, yes.
Hello? Hello?
We have a question from... Hold on. See, there's a time delay. So hold on to your question. Yes, you have a question in Stockholm. What is that?
The question is regarding the third home assignment.
Yeah, the first homework assignment, yes.
First or third home assignment? The assignment which is due on Thursday.
Yeah, there's another homework assignment due on Thursday. That was homework on Thursday.
The question is regarding if we solve the last equation to plot alpha versus q and we put CMACL is equal to 1, then MATLAB won't solve it because we can solve it only for CMACL is equal to 0, but not for CMACL is equal to 1.
Oh, really? And why is that?
Because there's a because if, we can't get a relation between Q and alpha.
Yeah.
Alpha and if we put CMS is equal to 1, then how do we get a relation between alpha and Q? That we are facing a problem.
Have you actually tried to run your? I assume you've written a computer code of some sort. Have you tried to run your computer code with that value of the parameter equal to 1?
No.
Have you done that?
No.
Well, then how do you know it doesn't work?
No, but I tried to first frame the equation, but I thought it would be a problem because...
you anticipated a problem. Well, my suggestion is you try it and see if it is a problem. Okay?
Okay.
Yeah. All right. Thank you. Now, Ricky, you had a question?
Would you like the code, the right code for the program attached with the homework, or do you just want the class?
Either way. If you've written the code, why don't you include it? That way I'll know you've worked hard and did something wonderful. Other questions? Okay. Here's what we're going to do in the next little while. We looked at that typical section with the spring and so forth and talked about divergence. But now we want to look at a configuration that's a little more like a real wing. And as we talked briefly at the end of last class, we're thinking of a cantilevered beam or plate with a flow velocity u. And initially, we're going to look at the case where it's clamped at this end and free at this end. Okay? Then, moving right along, we're going to look at a case where it's still a wing, But now at this end, we're going to put a spring, a torsional spring, okay? So in some sense, a little bit of a combination of what we looked at before. But this torsional spring represents, if you will, the flexibility of the fuselage or possibly even the windtunnel walls, or our windtunnel walls are pretty stiff. But if you had a very massive wing and the windtunnel wall was a little flimsy, you can imagine there's an equivalent spring. So we're going to put a spring at the wall. Sorry about that. We're going to put a spring at the wall. Okay. And initially, of course, we'll make it a layer spring. But then we'll make it a non-layer spring. And actually, I don't know if anyone's ever done the non-layer spring case, but you're going to be pioneers. You have the chance to do that. We might even put this in a journal article someday. So we're going to look at a layer spring initially, and then a nonlinear spring. And then the other variation is actually for all these cases, it turns out we've worked out more or less an analytical solution. As long as the properties of this wing are constant along the span. That's the sort of proviso. And as long as we use a simplified aerodynamic model. But then we would really like to be able to do the case where properties such as the core, the core changes to expand, or the distance from the elastic axis to the aerodynamic center would also vary if the shape of this wing varies with span. And for that, we'll need a different mathematical method, which is the one that people normally use in real life. So we're going to start out with a simple case and then build up to these more complicated cases. Okay? All right. So let's start out with a simple case. Simple case is everything's no spring. So here's simple case. No spring. Constant property of wings. And what I'll call simple aerodynamics. What I mean by simple aerodynamics, well, you'll learn about that later when we look at more complicated aerodynamics. You'll see it gets more complicated later on. So I'm starting out with the simplest one I think might provide some reasonable description of what's going on physically. Okay. So the first thing we need to do is develop the equation of motion, which turns out to be a differential equation. And then we need to solve that differential equation and identify the divergence condition, right? And we can do that. And the way we do that is we're going to use the principle of virtual work, which says an imagined change in the potential energy plus an imagined change in the virtual work due to the aerodynamic forces, more particularly the aerodynamic moment, must sum to zero. And from that, we will derive the differential equation, where we recognize that in our case, because my friend who's a structural engineer told me this is true, that the potential energy for a wing which is twisting about this axis, called the y-axis, is Gj, which is the torsional stiffness of that wing, times the derivative of the wing twist with respect to y, squared dy, integrated from 0 to small l, where small l is the span of the wing. I'm not going to use capital L because I want to use that for that. Although you note that I'm not so careful about using capital U, because I'm using capital U to mean potential energy. I'm also using capital U to mean flow velocity. But you will never be confused by the fact I use the same symbol to mean two different things, right? Okay, so we have that. And then the work, not the virtual work yet, but the work is the integral from 0 to L of m sub y times alpha dy. And the definition of virtual work is the integral from 0 to L of m sub y times del of alpha dy. It's the actual moment. The virtual work is the actual moment times the virtual change in the deformation, del alpha dy. It's only this definition that leads to the correct use of the principle of virtual work. Okay. So with that in mind, we can work out a differential equation. So the first thing we need to do, well, let's see these equation numbers too. First thing we need to do is compute del u. And del u is using equation 2, 1/2. Then there's a 2, right, because it's squared. There goes from 0 to L of gj d alpha dy times del of d alpha dy times dy. That's what we've done last time, and then someone pointed out that I eventually want to end up with an expression involving delta of alpha, not delta d alpha dy. And the way to accomplish that is to integrate by parts. Right? So if I integrate this by parts, thank you. If I integrate by parts, I'll get gj d alpha dy times del alpha, evaluated at 0 and L, minus d dy of gj d alpha dy del alpha dy. Okay? And I'm allowing for the fact that gj might depend on y. When I do the first simple case, I'm going to set gj to a constant, but I don't want to rewrite this equation of equilibrium every time. So I'm going to, at least when writing down the equation, I'm going to allow gj and other things to depend on y, and then I'll simplify when I actually try to solve the equation. Okay, we're all still here? Yeah, good. All right. So this is equation, whatever it is, 5. And now we're going to use 4 and 5 and put them into 1, and we'll have almost have our desired result. Okay? So now, 4 and 5 in 1 produces what? We have to take care of the minus sign, so I have minus gj d alpha dy del alpha 0 to L. And then I'm going to collect the terms that involve things under the integral. So I have plus d dy of gj d alpha dy. It gets multiplied by del alpha. But then I also have m's of y, which gets multiplied by del alpha, so I'll combine the terms that way, dy. Here comes the 0. And all of that, according to the principle of virtual work, must be 0. And then I say these magic virtual changes in del alpha can be anything I like. And therefore, if it's not 0 in particular, and it's arbitrary, the only way this equation can be satisfied in the interval between 0 and L is if this coefficient in the bracket is 0. That gives me my equation of equilibrium. So therefore, d dy of gj d alpha dy plus m sub y is 0 for all y, strictly speaking, greater than 0 and less than, greater than 0 and less than L. And then I want this to be true at y equals 0 and L too, right? And therefore this term must be 0. There are two possibilities. Recall that at the root at y equals 0, I said this is going to be quantum, right? So alpha has to be 0 there, right? And therefore, I'm allowed to imagine lots of things about del alpha. The one thing I cannot imagine the del alpha that violates a geometric constraint, to use the language of the subject. If I know something is 0, I'm not allowed to imagine it not being 0. Okay.
Is alpha, is it the flex angle, or is it like the change?
It's the pitch angle. So here's my way. I'm sorry, our friends in Stockholm can't see this. I'll do it for Durham, and then I'll imagine what we can do. So it's clamped, right? So we look at it. Twist about this side. Now, alpha is the angle twist about the elastic axis. And finding the elastic axis is normally something that a structural engineer does. If it's a simple uniform wing, it's also a bit more, right? But if the thickness or some other property varied along towards the elastic axis, it moves forward or back. In fact, often in helicopter work, they designed the elastic axis to get a quarter chord because that's also where the aerodynamic center is. And there's some benefits to landing at the elastic axis with the aerodynamic center. Remember, well, you'll come out of our mathematical analysis. There's going to be a parameter E, which is the distance between those two places. And when E goes to 0, the divergence Q goes to infinity. That's a good thing. If you don't want your wing to diverge. So it's a simple way to avoid divergence, at least within the framework of normal. So anyway, the boundary. So this is the equation of equilibrium. It's the differential equation of equilibrium. And the boundary conditions are alpha at y equals 0 is 0. But del alpha can be anything at the tip. Therefore, the only way this term can be 0 is if its coefficient is 0 at the tip. So at the tip, Gj d alpha dy at y equals L must be 0. The nice thing about the principle of virtual version is I'm going to give you the equation of equilibrium and tell you what the boundary conditions are, which may or may not be obvious, depending on your prior knowledge. Right? You can interpret Gj d alpha dy as the internal elastic moment that resists twist, right? It's sort of a spring constant. And if we had a spring, it would be K alpha times del alpha, and then the spring would have to be 0, but there's no material at the tip, right? So right at the tip, there's nothing to resist the tendency of this thing to twist. Therefore, that's what this boundary condition says physically. Or it just comes out of the background. Or both. Okay. Now, let's recall what m sub y is. M sub y, it depends on the aerodynamic theory you might be tempted to use. But the simple theory that we've been using so far is that this is the moment about the aerodynamic center, which again, in low speed flow, is used and for a higher aspect ratio wing is the fourth quarter, here the fourth quarter. And then there's plus the lift times E, which is that distance from the aerodynamic center. So this is the same aerodynamic model we used before. So we've complicated the structural model, right? But we've left the aerodynamic model alone for the moment. But later on we'll complicate the aerodynamic model. Okay, so this is now one. Keep track of my equation numbers. I'll call this equation 6. And these two boundary conditions together, I'll call 7. Here's my aerodynamic model. And then again, remember by definition, the moment about the aerodynamic center doesn't depend on alpha. And therefore, as we'll see a little bit later, the divergence condition doesn't depend on MAC, at least not within the framework of linear model. In fact, I'm going to set MAC 0 because of the simplifying line. And then the lift is for a static case. And now, these are moments in lift per unit span, right? Per unit span. So it's Q times C, not the area, but Q times C, which C is the force, times some aerodynamic coefficient, which is 2 pi or close to 2 pi low speed flow and something else in higher speed flow. And then I'm going to write this times alpha. That's the angle of attack in the aerodynamic sense due to twist. But then I'm going to allow, if you'll permit me, another alpha naught. Because I'm thinking of the case where I might have my wing at an initial angle of attack even before a twist. And then there's some twist because I'm loading the wing, right? So this is the angle of attack before twist, and then the full angle of attack is the sum of those two. So alpha is just the first part. And that alpha is the alpha that should appear in in the potential energy, because the potential energy only depends on twisting, right? It didn't, if I just take this wing and rigidly rotate it, that doesn't twist the wing. It doesn't elastically deform the wing, right? Okay. Very good. So now we're ready to do our analysis. And we're going to solve this differential equation, subject to these timing conditions, with these aerodynamic forces for moment sections. And the simplest thing to do is to assume everything is a constant and doesn't depend on y, right? Because then I'll end up with a differential equation which has constant coefficients. It's also linear, so you learn how to solve that in your differential equation, whenever you took that.
Yeah, the angle of twist is also the angle of attack here, or
the totaling of attack is the sum of the twist, which is alpha, plus some initial prescribed alpha naught. So you can think of alpha naught as the angle of attack at the root, right? I mean, this thing is clamped at the root, but then I can rotate the whole thing. Think of the root as also being the wind tunnel wall, so I could rotate this relative to the wind tunnel wall initially, and then I turn on the air, and then because I turn on the air, I have aerodynamic forces that gives me a further twist. Or you can think of alpha naught as being the angle of attack of the fuselage of a real airplane, right? And now alpha itself is the additional twist of the ring as it is loaded by those aerodynamic forces.
So there is an angle of attack because of the wing velocity, and also there is a twist angle.
Yes, right. There are two angles. That's right. Yeah. Another way to think of it is I just have this without any initial rotation, but then my aerodynamic flow is rotated, right? Either way. But that's alpha naught is. Alpha naught is the angle at the root relative to the oncoming flow. Right? But there's no twist at the root, no elastic twist. But along the wing, alpha is going to vary with y. I'm allowed to make all these parameters be constant if I want to look at a simple geometry, but alpha is going to vary with y. That's the whole purpose of this model, to allow for alpha to vary with y, to vary along the span. Okay, so I'm going to set MAC to D0 just for simplicity, and it is small typically, and it turns out the divergence condition doesn't depend on MAC anyway. And by the way, it'll turn out the divergence condition doesn't depend on alpha naught either. So I'm going to include that because I think it's a little easier to see physically what's going on if I leave alpha naught in. But if I already know what's going on, and I'm just trying to compute the divergence Q. If I'm a professional, I've been doing this for 30 years, I would set alpha naught to 0 because I know the divergence condition isn't going to depend on alpha naught. Okay. But I'll keep it in for a while. Okay, so putting that all together, what do we have? We have 6 plus 8 plus 9, and assuming GJ, etc. are constants, that is, they don't depend on y, right? Then I'll have GJ secondary of alpha with respect to y, right? Plus L, which is QC DCL D alpha times alpha plus alpha naught times E equals 0. Right? And now I like to non-dimensionalize, particularly when I'm doing simple problems like this, but even if I'm doing a real problem, I might be tempted to non-dimensionalize. Reasons I'll explain in a moment if it's not clear already. What I would like to do is I'd like to non-dimensionalize y by dividing by lambda. I could divide by the chord, right? But in this case, L is a little better because then y tilde goes from 0 to 1, and I'm going to integrate. And then I'm going to divide through by GJ, and I want these derivatives now to be respected by tilde. And so if I put 1 over L here, I have to put an L here, and then the second derivative is L squared. Right? If you do all of that, then I'm going to end up with alpha I'm going to use notation hat. What's hat mean? Hat means, by definition, it's the derivative, not with respect to y, but with respect to y tilde. This is a shorthand notation. Plus lambda squared times alpha plus alpha naught equals 0. And lambda squared is that thing that comes by dividing 2 by gj and taking into account the L squared and all that. So lambda squared is going to be defined to be, I'm going to have a Q and a C. I'm going to have a DCL, D alpha times E, and it's going to get divided by gj over L squared, which means the L squared is in the numerator. You can work that out. Right, if you don't. That's my note. I think I got it right. Okay? So now I put this in the most compact possible form. That's why I'm going to do this, right? So I don't have to carry along all those parameters. But once I find, I'm going to find out lambda. I'm going to find the magic value of lambda that corresponds to divergence. Once I find lambda, you tell me what all these parameters are, I can find Q, for example. Still with me? Stockholm, are you still there?
Yeah.
Good. I'm happy to hear that. All right. Now, so let's do a little analysis. Alpha double dash plus lambda squared alpha plus alpha naught equals 0. By the way, why did I make this lambda squared rather than lambda? Oh, I've done this before, and I know it's convenient to make a lambda squared. But I could make a lambda, and then later on I would end up with some square roots of lambda. But to avoid that, I do this. But you don't have to know that ahead of time. You can, right? But I did, so I took it out. Okay, what's the solution of this equation? Well, it's a linear equation with constant coefficients. And it's an inhomogeneous solution, inhomogeneous equation because they often are, right? So I've got to write this as the sum of a particular solution and a homogeneous solution. The homogeneous solution is A cosine lambda y tilde, now you see why I defined it as lambda squared, right? Plus B sine lambda y tilde. That's the homogeneous solution. And what's the particular solution? Well, this is a constant, which is the thing that makes it homogeneous. So the obvious thing to guess is to guess that there's a homogeneous, a particular solution that involves a constant. So if I add something that's a constant, when I differentiate a constant with respect to y tilde, I get 0. So all I need to do is make this term 0. Well, that looks like it's minus alpha naught, right? So the inhomogeneous solution is minus alpha naught. You may remember from difference equation course that if this alpha naught were a polynomial in y tilde, then you would assume in a particular form of the solution that was a polynomial in y tilde, and you would balance the coefficient. Right? If it's an exponential, then you got that's a constant. So now all I need to do is determine A and B, which I can do because I got two boundary conditions. That's all I need, right? I'm going to apply my two boundary conditions and what I do. Okay. So one boundary condition. Oh, see, this is the solution. I'm going to call this. I'm going to go back here. Oh, I'm going to go back up and I'm going to call that equation 11. This is still equation 11. This is equation 12. The boundary conditions are alpha y tilde equals 0 equals 0. What does that tell me? That tells me that A, this is cosine 1. A, this term is 0. A plus A minus alpha naught equals 0. I think that's what it tells me, right? So I now know A, it's alpha naught. That's good. Then I need to use the boundary condition D alpha C y tilde equals 0 or alpha slash equals 0 at y tilde equals 1. And what does that tell me? That tells me if I differentiate this, of course this term goes to 0. If I differentiate this, I get minus A sine lambda y tilde, but, oops, got excited. if I differentiate this, I get minus A lambda sine of lambda y tilde evaluated y tilde equals 1, so this is sine of lambda plus y lambda b cosine of lambda y tilde again at 1, so it's just cosine of lambda tilde, and that must be equal to 0, right? So this is equation 13. That tells me what A is, and this hopefully is not telling me what B is, right? Okay? Okay. So, let's see. I'm going to assume, although we've got to be a little careful, but I'm going to assume that lambda isn't 0, which in this case it turns out it isn't, but there are other cases where it might be, so we can't always assume that, but in this case. So then I have B equals A sine of lambda divided by cosine of lambda. But A, remember, is alpha naught. And this, of course, is just tangent of lambda. Okay, so now I know B, and I know A, and I'm done.
Equation 13, the boundary condition, it's f y squared equal to 1?
No, this is the boundary condition at y equals 0.
Yeah, but the line below is
this one. Oh, this is the y equals 1.
okay.
Okay. I guess I didn't really give that an equation.
Yeah.
You okay with that?
Yeah.
So now I found A and B, and now I just put it back in. I got alpha equals A, which is alpha naught cosine of lambda y tilde, and B is alpha naught tangent of lambda sine of lambda y tilde, and then minus alpha naught, right? I can take out a common factor alpha naught, which I want to do. And now I'll rearrange this a little bit. Let's see, what have we got? I've got cosine of y tilde, lambda y tilde plus tangent of lambda sine of lambda y tilde minus 1. Okay. So I'll stop here. And now, the question, folks, is it possible that alpha gets pretty big? Like, goes to infinity? Yeah, that's very good. So, when does this thing go to infinity? Well, let me remind you, the tangent is the sine over the cosine. Cosine doesn't go to infinity. Sine doesn't go to infinity. 1 doesn't go to infinity. Sine doesn't go to infinity. But cosine doesn't go to infinity either if it goes to 0. And this is the denominator. So when cosine goes to 0, alpha gets pretty big. And note that that condition does depend on alpha naught. So if I wanted to, I could have thrown alpha naught away at the very beginning and treated this as an eigenvalue problem, which I'll do in a moment, and gotten the same result with less algebra, but also perhaps with less physical understanding. Okay. So cosine lambda equals 0 gives me the divergence condition. Well, how many values of lambda are there for which cosine of lambda is 0? Pi over 2. So this lambda could be pi over 2. It could also be what? 3 pi over 2. And what else? 5 pi over 2. And in general, it could be 2n minus 1 over 2 pi, right? Where n goes from 1 up to infinity. Well, I have an embarrassment of riches. not only did I find a divergence condition, I found an infinite number. Is that a good thing or a bad thing?
Very obvious.
No, it's not a bad thing. Which one represents the physical divergence condition? It's pi over 2. Pi over 2, right? Because lambda, remember lambda squared actually. Lambda squared is proportional to Q. And so I'm thinking physically, I'm going to increase the dynamic pressure. I'm going to increase 1/2 remember what Q is? It's 1/2 the density of the flow times U squared. Actually, I'm going to put a subscript on that, and then you wouldn't confuse it with potential energy. Okay, so I'm thinking of finding my model in the one solenoid, I'm increasing the flow velocity, and when it gets to when in non-dimensional terms lambda gets to pi over 2, I expect to get a very large alpha. Okay. What happens beyond that? Well, it's interesting mathematically, but by the time I've done to that big a twist, my mathematical model is no longer really a very good model because I've probably damaged the wing. Right?
It doesn't depend on alpha naught. It doesn't.
Well, yeah, how big alpha gets depends on alpha naught. If I wanted to plot alpha as a function of lambda, I could do that, right? It's only when I get the lambda equal to pi over 2 that the alpha is going to go off to infinity according to this math model. But that just brings the math model picking down. But it's good enough to tell me that there is a value of lambda or a value of dynamic pressure when the alpha is going to get very big, and I probably don't want to test my model too close to that value. Right? Not without risking damaging the model. Or if it's a real airplane, risking damaging my airplane. Okay. What about all the other lambdas? Well, it turns out they're useful, as we'll see next. Believe it or not, they're useful mathematically, even if I want to only find the divergence condition. In the case where now I'm going to allow my properties, like the core, the TJ, and those other things, E, I'll allow them now to vary with Y or Y tilde. But I'm going to use the information I gained from this simple analysis to address that more complex situation. Okay, one final thing. If I look at this equation 15, remember this is going to infinity. This term goes to infinity, right? Therefore, that means this term is really a lot bigger than 1. It's a lot bigger than cosine. That tells me what the twist shape is. It tells me how alpha varies with Y tilde near the divergence condition, right? Because this term is going to dominate, so it's going to go like a sine wave, right? That's what this analysis tells me. Of course, if I'm below the divergence condition, then the cosine and the 1, they all contribute. By the way, you should verify that alpha is 0 and Y tilde equals 0, right? This is 1 minus 1, 0. This term is 0. So everything's fine.
Why would you care the shape of this one?
Say again.
Why do you care like the shape of?
Why do I want the shape?
Yeah.
Well, because for several reasons. Not the least of which is, I may not be really all that confident in my math model, and therefore, when I make my measurement, not only do I want to measure the divergence condition to compare to what my math model predicted, I want to compare the shape that my math model predicted. Because if it happened to predict the right divergence condition but the wrong shape, that would not make me feel warm and fuzzy about my math model. And not so much in divergence, but flutter, which is sort of the dynamic counterpart. It's been known people will predict the flutter speed pretty accurately, but they get the wrong mode. Okay, and that usually, so that's sort of luck, right? But if you get not only the right divergence condition, the right flutter condition, and you also predict the correct shape. In the case of flutter, you also have a prediction of the frequency. Here, there's no frequency, it's static, right? But when you're comparing theory and experiment, you want to compare everything you possibly can, including the shape of the deformation. And if everything lines up pretty well, between what you measure and what you calculate, then you think, I must have something that's pretty good. So it's the confidence level to look at the shape and compare theory and experiment. Okay. Moving right along. Any more questions? Stockholm, any questions from you?
No.
Okay. So let's now do the general case. Where's the general case? Let me go back. Let's see, where's my wonderful equation? Here it is. What I mean by general case? I want to do the case. Next case. It's not the most general case, but it's fairly general. Now I'm going to let Gj be a function of y, and C be a function of y, and D be a function of y, and I might even let DCL D alpha be a function of y, right? Everything can be a function of y. It turns out, if you're going to let one be a function of y, you might as well let them all be a function of y, because it doesn't make life any harder. But here's our differential equation now. It's d dy again. Now Gj d alpha dy plus m sub y, and I'm going to set MAC to 0 again just for fun, for simplicity. So I get QC DCO d alpha alpha plus alpha naught E equals 2. I'm going to call that equation 16. Well, in general, unless these coefficients have particular dependencies on y, I won't be able to solve this equation. I mean, there are things like Bessel's equation. Remember Bessel's equation? Bessel's equation is an equation with variable coefficients. So if I wrote down Bessel's equation and then very clearly chose Gj and all these other things to line up the same coefficients, Bessel's equation, I could cite this in terms of Bessel functions. Or more generally, there's something called hypergeometric functions, which are various equations for which analytical solutions are known when the coefficients depend on y. But, people don't necessarily build airplane wings just to line up a Bessel's equation. So we want to do it in our general case. So what we're going to do is we're going to use a method called modal analysis, which you probably have encountered in the case of vibrations. Okay. So we're going to take alpha of y, and we're going to assume that's a sum of terms. I'll call them a sub n. These are some coefficients we don't know, but hope we determine. Times some functions alpha n of y, where I'm going to choose these functions. And what should those functions do? Well, they should satisfy the boundary conditions. But they also, and in some sense, they should satisfy the different equations. If they satisfy the equation of interest, it's done, but I'm not going to be that lucky. So what do I choose? I choose the functions which satisfy this equation in a special case where all the coefficients are constant. Now, what are those functions? Well, they are the functions that go along with the values of lambda, which make alpha go to infinity. Remember we said there was a lambda equals pi over 2, which is the most interesting one. But there's also a 3 pi over 2. There's a 5 pi over 2, and on up. And by looking at that equation, we saw that there was a shape function which went along with this, right? And the dominant shape function was sine lambda y tilde, right? Out of all those terms in the equation, the dominant term, this was the dominant term in terms of the shape. But now, I have also a series of functions. I have sine pi over 2 y tilde, sine 3 pi over 2 y tilde, and so forth, right? So now I'm going to use all those other functions. Okay, I'm going to use all those other functions. Because the real shape for the case where these things vary with C, vary with lambda tilde, rather, the real shape now for that case will not just be one of these functions, it will be some linear combination of all the functions. Now, if you've done this before, or maybe even think about it a little bit, you might anticipate that this function will be the dominant function, but it won't be the whole story. But then these other functions will be, if you will, corrections to account for the fact that Ej and these other parameters vary with y tilde. So that's what we're going to do. Okay, now, so this is equation 17. So I'm going to take this and put it in here. And the goal now will be to determine case of n. The simplest thing to do is just to use one function. It's one term in the series. Right? But in general, I will get a better answer if I retain more than one term. In fact, if you're careful and conscientious, you'll do a one-term solution, then you'll do a two-term solution, then you'll do a three-term solution. And at each stage, you'll find dynamic pressure at which divergence occurs. And you'll see if, as you retain more and more terms, you see a convergence. You know, the three-term solution, two-term solution are virtually identical, in which case you stop. You certainly don't want to include an infinite number of terms, right? Even with a modern computer, an infinite number of terms takes a while to compute. Typically, 4 or 5 terms will give you a great answer, and one term usually isn't too bad. It depends on the situation, but even one term will give you a ballpark answer. So let's do that. So we're going to put 17 and 16, and I'm going to get the following. dy, all these is in dimensional terms, or we could do it in non-dimensional terms if you prefer. dj d alpha dy, oops, dj d alpha dy will be what? We'll get the sum over n of a sub n d alpha n dy, right? I just take this thing and differentiate with respect to 1. So I get that plus qc dcl d alpha summation over n summation over n d sub n alpha sub n times e equals 0. So that's 18. So now I have to make a decision. By substituting 17 into 16, I produce one equation, but in general, if n goes from 1 to 17, you probably don't need 17, but let's just take it as an example. If I took n equals 1 to 17, I have 17 unknowns and only one equation. That's not a good situation. I generally would like to have the same number of equations as unknowns. So I can do one of a couple of things. Let me tell you, first of all, a thing I would not recommend you do, but you could do. You could pick 17 values of y between 0 and L and ask that this equation be exactly satisfied at those 17 points. That would give you 17 equations and 17 unknowns. I, in principle, could use matrix algebra to find a sub n. Right? That's usually not a good thing because while you satisfy the equation at those 17 points, in between there will be usually fairly substantial variations that are not good. You generally want to use a smoother technique. And the smoother technique is due to coercion. It was a Russian railway engineer around 1890 who wasn't solving this equation. He was solving some other equations, but similar situation. And Griffith said, well, why don't we do this? Let's take this equation, which is only one equation, and let's multiply it by something and integrate it over the span of the wind. Well, first of all, multiply it by alpha 1, the first term of the series, and integrate it. Right? If we do that, then the y variation goes away because I'm going to integrate over y. That's one equation. Then I'll multiply by alpha 2, and I'll do it again, and then by alpha eventually up to alpha 17, and now I have 17 equations and 17 unknowns. That's the way I go. So Goyle's method is a method used in lots of different places in engineering and science. There's another method called the Rayleigh-Ritz method, which I'll mention a little bit later, maybe today, which is similar but a little different. So we're going to use the Rayleigh-Ritz method. So I have to sum over n. So I'm going to I could go through laboriously and multiply 2 by alpha 1, alpha 2. So I'm just going to multiply 2 by alpha sub I. And I'll call it alpha sub I because I don't want to confuse it with n, right? But then I only need to do at least conceptually this integration was wrong. So we're going to multiply 18. Okay. We're going to multiply 18 by alpha sub I, where I also goes from 1 up to 17, right? Or whatever the total number of equations, and integrate from 0 to L dy. And that will give me what I want. So what do I have? Let's see. I'm going to have summation over n, and now I'm going a sub n. I'm going to work on the first term. And I've got the integral from 0 to L of d dy of tj times d alpha sub n dy times alpha sub I dy, right? That's the first term. And then the next term, it will be right here. Q doesn't depend on y, right? That's one of the few things that doesn't depend on y. Yeah, it's just 1/2 the density times the closest. So I can take that outside here. So now I have an integral from 0 to L of C dCl d alpha times E. Everything's going to have, all of this is going to have an A sub n. And now I have alpha sub n, alpha sub I dy. Okay, so that takes care of this term, and this term, and I did something I should have done. Well, I didn't put in alpha naught. But if you'll permit me to, I think I'll just leave it down. Why? Because in my simpler model, I discovered that alpha naught doesn't really enter in divergence. If I really want to know how alpha varies at all q's, not just at divergence, but at all q's, I need to include alpha naught, right? But right at divergence, the divergence condition doesn't depend on alpha naught. So hopefully I can take advantage of that in this situation.
I mean, as long as alpha naught is not 0?
Well, I am implicitly assuming it's not 0. It could be anything. Not quite 0.
Okay.
All right.
So, like alpha naught, is just alpha as the root of the mean, or could it be like alpha naught a function of y, like it's the first three.
The alpha naught itself could depend on y.
It can depend on y.
Yeah, and if I want, if you absolutely insist, I'll put the alpha naught back in. You don't insist? Oh, that's very kind. Thank you, very kind. Okay. Now, this thing in brackets, it's a mess, but it's not too bad. For simplicity, I'm going to call this K sub n I. And it's a constant, right? You tell me what GJ is. I know what the functions are, right? I've chosen those. So, it's just a constant because I've integrated such a y. It doesn't depend on y naught, right? And this thing, I'm going to suggestively call it A sub n I. Again, it depends on you see all the alpha and all that, but it's just a constant, right? Okay. Are you still with me? That's good. Thank you. So now, say again? Yeah, the whole thing is still equal to 0. But remember now, there are 17 equations. This is really 17 equations, because I can be 1, 2, 3, 4, up to 17. So now I'm going to write this in matrix notation. I'm going to write this as a matrix K plus another, plus Q. Q is a constant that comes out in front, times another matrix A times a common matrix of these A's equals 0. So this is, I'm going to call this equation 19. 19 is the equation I just wrote down. So this is 19 now in matrix notation. Okay? Well, this is a set of linear algebraic homogeneous equations, and one postulation is that all the A's are 0, which would imply that alpha is 0. That's not a very interesting solution. The interesting solution is when A is not 0, and the only way A cannot be 0 is if the determinant of this entire coefficient be 0. So this determinant depends on Q. And there are only 17 values of Q for which this determinant is 0. But again, it's golf. If you're a golfer, the lowest Q wins. The lowest Q is the physical divergence. And that's the eigenvalue way of thinking about divergence. That's the way it's usually done professionally, because why bother to carry along alpha naught when you don't really need it? Again, if you really want to know how alpha varies Q for all Q's, not just the divergence Q for all Q's, you needed to carry alpha naught through, which you could have done. All that would have done is make the right-hand side not 0. If the right-hand side is not 0 because alpha naught is not 0, then you think of divergence as, under what conditions will the A's go to infinity? The answer is the same. It's when the Torsional coefficient equals 0. So whether you think of it as an eigenvalue problem or as an inhomogeneous problem, by retaining alpha naught, by divergence, you get the same answer. And this mole analysis is the standard way of doing it. Normally what you do is you determine a basis set, or a mole set, from some strong structural analysis. In this case, we actually determined it from an aeroelastic analysis. When we do dynamics, you'll see that what we normally use for the modes are the natural vibration in vacuum modes. We don't use the aeroelastic mode for a simple case. But whatever modes you use. And part of the skill set of someone who does this professionally is choosing the right modes. And normally you're choosing modes which are simpler, or the solution to a simpler but related problem. In this case, it was a problem of constant properties along the span, right? And then we use it to do the case where the properties vary along the span.
You said you use in vacuum modes to do what?
Oh, I'm sorry, to do flutter analysis.
Okay.
Okay. We haven't gotten there yet. I'm giving you a peek. It's coming attractions. Okay. You could actually use the vector modes to do the divergence now. All you need is a nice set of modes to satisfy boundary conditions, and the natural vibration modes of this torsional structure are a perfectly good set of modes. That would be another set of modes. Remember, at this point, all I said is I'm going to use some modes. These equations are the same, whatever modes I use. The only thing the difference is these coefficients of the A matrix and K matrix will change if I use a different set of modes. Right? But the form of the equations will be the same. And it's not unknown sometimes that people will try different sets of modes to see which one is best. And best is normally determined by, it's the set of modes that gives you the quickest convergence. And one set of modes requires 17 terms to give you a good answer. Another set of modes only requires 3. Which set of modes do you like? Well, I got the ones that give me a good answer for them.
How do you get another set of modes?
Well, in this case, we use what I call the aeroelastic modes, right, of a simpler divergent problem. Okay? We could do that. Another set of modes would be to use the natural modes, the natural vibration modes of the structure, which we could do that too. Want we talk about that for a little bit? I'm not sure.
I'm not sure.
Okay. We'll come back to that later, but not today. We'll talk about that when we get into dynamics. What you need to do is you need to add the inertia term, right? You need to add a kinetic energy or the inertia term or acceleration terms. And then you could find the natural modes of this structure, and you can use those ones. And again, you probably wouldn't use the natural modes. Well, you have two choices. You could use the natural modes of the constant property plane, which would be easy, relatively easy to determine. Or you could run a finite element code and find the natural modes of the variable property plane and use those modes to do the divergent analysis. So there are several choices. And part of the art is deciding which set of modes to use. And sometimes in that case, there may not be entirely sure which one would be better. They all should work if you use enough modes in the series. But the key is to make sure the modes, whatever modes you use, satisfies the boundary conditions. Because you notice that in this method I just used, there was no way to satisfy the boundary conditions unless I allowed each function in that series to require each function to satisfy the boundary conditions. Okay?
The only scheme again between the set modes is the one that requires less modes to perfectly describe the motion.
Say that one more time.
If we can have more sets of modes and they all give us the same result,
Yes.
we will pick the set of modes that has the lowest number of modes,
right.
so that we can have like coverage and cheaper calculations.
That's what most people would do. I mean, there might be some other special consideration in some particular case, but normally we're looking for the set of modes that give you a good answer with the smallest number of modes. So people talk about a rapidly converging series. I mean, anytime you use mole analysis, if you're reasonably conscientious, you should try it with different numbers of modes and make sure that the answer you get is not changing as you continue to increase the number of modes. Okay, let's see. Okay. Oh, it's time to sign a homework problem, right? I'm glad you suggested that. I probably would have forgotten if you hadn't mentioned it. Okay, so homework number 4.
Yeah.
Homework number 4.
So we have homework every class. Are you complaining?
I have a colleague on the faculty. I won't mention his name so you won't throw rocks at his door. He says students are the only customers he knows who want less of the product, at least in terms of homework. Okay. Anyway, homework number 4. Let's do the following. Let's now put that spring at the root, right? There's it, right? So we're going to put the spring at the root. Choose it. And what does that do? If I have this torsional spring at the root, and now let me look at this way, right? And at the root, I'm thinking of now there's a torsional spring, just like we had before, right? You can call it case about. Now, but I still have a wing, but now there's a spring, but just at the root. I mean, I could put it anywhere, but the root is the physically interesting place to put it. How does that change things? Well, now the potential energy, which includes, of course, still the same things before. Now I have 1/2 K alpha. Alpha evaluated not anywhere, but where the spring is, right? That's all I do. I just add in the potential energy associated with that spring. Now, you can do one of several things. The homework assignment is go back to the constant property case and work out the convergence for the constant property case. So, for the constant property case, and you probably want to non-dimensionalize and define lambda and all that good stuff. Find the divergence condition. I would suggest you still define lambda as what it was before. What was lambda? My definition of lambda, here it is. Lambda is still going to be QC DCL, E alpha, E L squared over EJ. But there's going to be another parameter, which is essentially going to be the ratio of this stiffness of the string to the stiffness of the wing. And I think I'm going to call that K. And what is K going to be? It's going to be K alpha. Let's see. It's going to be GJ. I think it's going to be that. But check me on that. This is small L. How do I know that? Well, the way I would know that is I would take this expression for potential energy and non-dimensionalize it. Right? I would non-dimensionalize Y by L and so forth. So if I did that, you would get a non-dimensional ratio of this term to this term. Alpha itself, of course, is already non-dimensional. So I think that's what you want to do. So it would be easier for me to grade the homework if we agree on the notation. But the nice thing about this is, I mean, if you do it this way, then you realize that the solution doesn't depend on all these things independently. It only really depends on two parameters. It only depends on lambda and K. Right? So if I work out the solution for lambda and K, I'm told that, in fact, if I find the special lambda corresponds to divergence, lambda divergence only depends on one parameter. K. Before it was just pi over 2, right? Now it's going to be something involving K. But you can do it. Now, in this case, you should be able to work out exactly by solving the differential equation and all this the same. But you can also do a mole solution. Another thing you could do is use a mole analysis. Okay. But don't use the modes that we just determined when K was not there, because you'll get a bad answer. And if you can tell me why you get a bad answer using those modes, you get a prize. What's a prize? Okay. All right. Yeah, I think I'll stop here. We've got 5 minutes more. But, at the start of next class, we'll talk about Rayleigh-Ritz. If you've not encountered Rayleigh-Ritz before, Rayleigh-Ritz. That's Lord Rayleigh, who wrote the theory of sound in 2 volumes, did lots of other amazing things. Ritz from Germany, and Rayleigh came up with sort of the initial notion, and then Ritz exploited it to a greater degree. So usually both names are attached to the method. The nice thing about the Rayleigh-Ritz method, despite my admonition about assuming that the modes you use are not assuming, but requiring that the modes you use satisfy individually the boundary conditions. In the Rayleigh-Ritz method, you can dispense with that requirement. Or I shouldn't say you can dispense with it completely. The modes still have to satisfy the geometric boundary condition. Namely, in this case, the one at the root, this is alpha 0. That's got to be true. But you don't have to satisfy the other boundary condition, the one at the tip with your modes. And sometimes that's a nice thing to exploit. Mostly people use modes, even in Rayleigh-Ritz, as we'll describe it, that satisfy all the boundary conditions. But strictly speaking, you don't have to satisfy all the boundary conditions mode by mode. They have to sum up in such a way that they, to a greater approximation, collectively satisfy all the boundary conditions. But they don't have to satisfy the boundary conditions individually. So we'll talk about that next. Any questions before we conclude for the day? Stockholm, any questions? Hello? No, I can see them. They're still there. Thank you. Now, while you're starting to work on your homework tonight, what else are you going to be doing? Watching the game. There you go. Just want to make sure your heart is right there. Are you going to the game tonight?
Yeah.
Are you really? How do you get tickets to every game?
Graduate count out at December.
Well, I thought you had to split them with your colleagues or something.
Yeah, with this one. Other graduate students we got full day.
Okay. All right. Okay, I'll wave at you.
What section are you?
I'm in section 8.
You're in the bottom. 6, 7, 8.
I'm behind the opposition bench, about halfway up.
Yeah. All right.
Okay, good.
Professor, when is this homework due? When is the homework for you?
Oh, a week from today. All homework is due a week from the day of the
There'll be a assignment. There'll be an assignment.
Oh, thank you. Okay, good. All right, very good.
All right, so think about who's winning.
We'll cut lines that can move from your bench to the other bench. When you could winning. Okay. You know, we're going to get here. Thank you.